Okay, introduction to vectors. Mass of a rock can be expressed by a single real number, length of a field also by a single real number. Such quantities are known as scalar quantities. A scalar quantity has only magnitude and is specified completely in size by a number. So a football field is 110 yards long. Some physical quantities cannot be completely specified by magnitude alone. A force acting on an object is not completely specified by stating only its magnitude. We must also know the direction in which the force is acting. Such quantities are known as vector quantities and must be specified by a real number called the magnitude and by a direction in space or beyond. If it's in 4 or 5 dimensions, then in 4 or 5. Representing vectors. Vectors can be described geometrically, algebraically, or as a column matrix. Geometric vectors. Vector may be represented geometrically with a directed line segment. What's directed mean?
In a direction.
It's going in a direction, yeah, right? It's got an arrow, but only on one end, because it's got to say it's going that way. Drawn to a suitable scale. Such vectors are known as geometric vectors. Some examples are shown below. Naming vectors. Vectors may be named using 2 letters, A, B, with an arrow on top of the line. It's not really a big arrow there. On top, indicating the direction is from A to B. You might see it as a double-headed arrow. You may also see it written with a single-headed arrow, which is generally easier to write if we're writing them right. But either one is correct. It indicates, in this case, the direction is from A to B, right? Using a bold-faced single letter, like U, bold, right? You're not going to do that by hand, so not by hand, right? Not by hand. So you will not be indicating any vectors this way. I will indicate them like up here. You see the U, right? That's fine. You'll see it in print that way. You can't do it by hand, so don't. Using a single letter V with an arrow on top, that's how you do it if you want to talk about vector V. And again, that is actually an arrow on top. Could be double-headed or single-headed arrow. It doesn't matter. I tend to write them single-headed. It's easier. The magnitude vectors, do you know by using the symbol? We've seen this one before?
Absolute value.
Absolute value, right? Which in this case means the magnitude or size of the vector, right? Means we strip off the dimension. So it could be AB with arrow on top, right? Boldface U, or V with an arrow on top. Draw a circle around the vector that has the same magnitude and direction as V. So up here, which one has the same magnitude and direction as V? The one that I just circled, because it said draw a circle around it. Draw a rectangle around the vector that has the same magnitude of V but does not have the same direction. What's the same size but not the same direction? One that this arrow is pointing at. Okay, draw, what are we drawing? I gotta open this up. What are we drawing next?
Draw a triangle and rectangle.
Now, the same direction as AB, but not the same magnitude. What's going in the same direction as AB? Underneath what?
The first one.
And what are we drawing around this? Okay, so there we go. Okay, triangle. Are we drawing anything else?
Draw a vector.
Draw a vector that has the same direction as V, but 3 times the magnitude. So what would we draw?
3 times as long. What?
Okay, so, you know, you got to do your best to estimate, but, you know, if we had a ruler, we would measure it out, and then we would measure the line that we're drawing. And what's special about V and the vector that's 3 times the magnitude, but the same direction? Kind of long. They're parallel, right? Yeah, they're parallel. So if you're going in the same direction, then you'll be parallel. Draw vectors that have the same magnitude as U, but in the opposite direction. So what are we going to draw?
Just one flip. Yeah,
Made it a little too big. Okay. All right, good? Yeah, so far so good? Okay, let's move on to page 2 of 26 pages in this thing.
26?
Well, we're not doing them all today, but we have to get through a substantial number. Algebraic vectors. Vectors in a plane can be described in terms of a basis. The most commonly used basis for two-dimensional vectors is I and j, as shown below. So I is what we would have called the x-axis, and j is the y-axis, right? So note that I, the vector I, that's the basis vector, is 1 unit to the right, and the basis j is 1 unit up. If vector v is 3 units to the right and 2 units up, 3 units right, 2 units up, it can be expressed as 3i plus 2j. Okay? The vectors 3i and 2j are called the components of v. The vector u is 4 units to the left and 6 units down. Then u can be expressed as negative 4i minus 6j. State the components of u. So, what are the components of u?
Minus 4i.
Minus 4i.
And minus 6j.
Okay?
Yeah.
So they have signs associated with them, right? I mean, what does negative 4i say? Which way is he going?
Go left.
Go left. And negative j says? Down. Okay. Vectors in three-dimensional space can be described in terms of the basis I, j, and k, where k is perpendicular to the plane containing I and j. At that point, usually I and j become flat, and k runs perpendicular, so up or down, right? An example of a vector in three-dimensional space is 2i plus j minus 5k. The components of this vector are
2i.
j and negative 5k, right? I'm supposed to put arrows on all of these. Oh, really?
Oh, I actually did that.
Did you? Good. I'm out them one-sided because it's easier to draw them one-sided. I don't have to lift my pen or retrace any lines. The vector A is equal to 3i minus 2j can be expressed as the column vector 3, negative 2. The vector B, which is equal to 5i plus 7j minus k, can be expressed as the column vector 5, 7, negative 1, right? So in this case, you're just reading the column. This is the I, this is the j, this is I, this is j, this is k. 4 dimensions, we get L and M and N and O. Go on and on and on. Equality of vectors. All vectors are created equal except for those that aren't. Two geometric vectors are equal if and only if, biconditionally, they have the same magnitude and the same direction. Note that the position of a vector is irrelevant. So where it is doesn't affect whether it's equal to something. So what is equal to you? The third one.
Yeah, the third one.
And I'm not circling them, I'm ellipsing them, but it says circle, but really. It's an ellipse. Otherwise, I'd have to draw something this big. Negative of a vector, or the additive inverse, right? There's no such thing really as a negative, it's the additive inverse. The negative of a vector u is a vector equal in magnitude to u, but with a direction opposite to u. The negative u of u is denoted by negative u. I know, it's kind of really. The vector v is shown below. Draw negative v. So how would you describe those two line segments? They're parallel, right? But the arrows indicate they must be in opposite directions, so that one is the negative of the other. The negative of AB is BA.
No.
I think that's the statement, right? But it just says, again, it's position, right? It doesn't matter where the position. This vector could be here, it could be down here, it could be over here, it could be up there, it could be off the board over there. Note that if v is equal to negative 2i plus 8j, then negative v is equal to positive 2i minus 8j. You're just going to change the signs. If u is 3i minus 10j, then what is negative u?
Minus 3i plus 10j.
If u is equal to 6 negative 5, then what is negative u?
Negative 5, 6. Negative 5, 6.
Negative 6. Negative 6, 5. Negative. Yeah, wait.
Why did I listen to you? Just because you get high marks? No, it's negative 6, 5. You are negating, right? We're not flipping. We'll do that later. There's some operations you can do with that kind of stuff. Scalar multiples of vector. If a vector is multiplied by a non-zero real number k, then the vector ku has the same direction as u if k is greater than 0, and the opposite direction as u if k is less than 0. The magnitude of ku is the absolute value of k times the magnitude of u. That is, the magnitude of ku is equal to the magnitude of k times the magnitude of u.
What?
No.
Want me to just read that again?
Yes, Chris.
Why?
If you multiply a vector by a number, you're going to get a scalar multiple. If that number is positive, the scalar multiple will go in the same direction as the original vector. If the number is negative, the resulting vector will go in the opposite direction. That's really all that says.
And why use a fancy word? You're confusing everyone. No, it's fancy word.
Yeah. Should we use French? Vector u, 3u, and negative 1/2 u are shown below. So you notice u and 3u are going in the same direction, and that 3u is 3 times the size of u, and that negative 1/2 u is pointing in the opposite direction and is half the size of u. You need to draw 2u.
Oh, so funny.
And negative 3/2 u.
That's
Why
a
is
little long.
3 halves the same as 3?
It's a little long.
No.
Not one.
But vectors have to be proportional. That's the whole point.
Yeah, well, you do it on yours. You got a ruler.
Well, you have to make them relative.
Oh, you might want to bring a ruler.
Oh, okay.
But I wouldn't worry too much about it. I mean, if you want to draw diagrams accurately, then okay, obviously the ruler helps, right? But you know, we're going to be doing most of this algebraically anyways. If a is equal to negative 3i plus 2j, then 4a is equal to 4 times that, which is negative 12i plus 8j. If b is equal to 4i minus 5j, determine 3b.
12i minus.
So 3 times 4i minus 5j, which is 12i minus 15j. And negative 7b is, squeeze that here. Okay, all good? Yeah, got that figured out? If u is equal to 6 negative 5, then negative 4u is negative 4 times 6, and negative 4 times negative 5, or negative 420. Determine, state. So what's 2v?
4 negative 6, 14.
And what's negative 8v?
Negative 16, 24.
56.
Negative 56.
This number, negative 50.
Yeah, so far so good. You'll stop me if you have any problems?
Yes.
Okay, and I'll just blow you off and continue on because there's now time. Vectors are said to be parallel if and only if, another biconditional, the vectors are scalar multiples of each other. That is, u is parallel to v, then u is equal to kv. If u is 6 negative 5 and v is 2a and u is parallel to v, then what is a?
Negative 5.
Negative 3, negative 5.
How'd you get that?
What? Yeah, how do you
What?
get it?
5.
Isn't it?
Yeah, 6 divided by 2 is 3. Negative 5 divided by 2 is negative
You don't get this?
Yeah,
Three.
it's,
Negative 5
yeah.
over 3.
Yeah.
Round about 1.
Yeah, negative.
See, I was right.
Okay, what he said. Long time ago.
What?
Are negative 4, 5 and 20.8 negative 24 parallel?
Oh, God, are they?
If they're
I
the
need my
same,
calculator.
if they're multiplied by the same.
If they're multiplied by the same thing, they are. So are they?
Yeah. Does it?
I know,
Is
I
it?
need calculator.
I know.
Sure. Calculator.
Negative 1.2.
20.8.
No, I don't.
I don't think they parallel.
I don't know.
How?
Yeah, no.
No, they're actually.
Wait, where do you get 4.2? Negative 4.2? Negative 4.
Oh.
Yeah.
Law.
So what is it? 5.2?
Yeah.
Yes.
And what was it?
So not parallel.
If it was negative 26, it would be.
Yes, it would be.
Yes.
Okay, so not parallel, right? They're not scalar multiples of each other. Addition of vectors. Geometric vectors. Geometric vectors can be added tip to tail. If u and v are two vectors represented by directed line segment PQ and QR respectively, so that the endpoint of PQ is the initial point of QR, because it's starting with Q, so starting at Q, then the sum of u and v is represented by the vector PR. So this is like, if one person walked to here and then turned and walked to here, the other person could get there simply by walking along. U plus v. Yeah, it's a displacement, right? So think of it as a displacement. Okay, so how far am I from the starting point and in which direction? That's what this is here, which is u plus v. Yes? No?
Yes. Please.
Geometric vectors may be added by placing the tip of the first vector at the tail of the other vector. It's known as the tip-to-tail method, as shown below. So we have these two vectors. We move vector b. It doesn't really matter where vector b is in the plane. We can shift it as long as it remains the same size and magnitude, right? Magnitude and direction, as long as it has that. Okay? And then the sum of the vectors is beginning at the tail of the first vector and going to the tip of the second vector. So here's a plus b. Use the tip-to-tail method to draw the sum of the following two vectors. Now, you can do either one, right? You can move D onto C, but that'll get kind of messy because it'll be over there. We'll be drawing on top of the drawing. So I'm going to take C, shift it down and over, keeping it C.
Close enough.
I redo the whole thing.
Right? So there's C, and then this is C plus D.
Why don't they have arrows on them?
They are bold letters, and if you'd been paying attention at the beginning instead of not paying attention, then you would know. So that's why I'm always drawing everything with an arrow on top, because I can't draw in bold, right?
You're a smart one.
Because I'm not going to allow you to draw in bold, and therefore I will not draw in bold. Vectors may also be added by placing the two tails together, forming two sides of a parallelogram. The sum is the diagonal with the common tail of the resulting, so starting where the two tails join together and then going across diagonally, right? So really, it's as if you placed B here, right? I mean, here's B. If you just had put B there, then we would be doing tip to tail, right? But we put the B together there. The way we can think about this, so the first one we thought of as a displacement, right? Because you move it, and you say, well, you're walking here, and then you're walking there. That you could do. The second one here, think of as like an airplane flying, and here's the wind blowing. In that case, it's really acting on the same object, right? So we need to draw this as a parallelogram, as opposed to think, well, okay, airplane flies here, then wind blows it there. It doesn't happen in real life, right? I mean, it moves. What happens is the airplane actually moves along this path. Okay, so if these were velocity vectors, you think, well, the airplane's flying with this velocity, wind's blowing with that velocity. Here's the resultant velocity, right? It's the vector sum. Use the parallelogram method to draw the sum of the following two vectors, right? So we can just start with D and we can put C here. So we put the two tails together and we draw a parallelogram. So I'm going to draw a C off of here. I'm going to draw a D off of here. And there's C plus D. Okay, so far so good. Yeah? Ready to move on? Short day, long time. Short period. Subtraction of two vectors can be seen as the addition of one vector to the negative of the other vector. So if we want to do u minus v, we can do u plus negative v. So we're still going to add, but we're just going to change the direction of the second vector we're adding. Vectors c and d are shown below. To draw c minus d, we're going to add c to negative d. So here's c, and then we put in negative d. Now where do you start? You start at this tail, and you go to this tip, right? That's the direction we're going. So we're going c minus d, right? There's vector c, then vector minus d. Okay, which gives us basically c plus minus d, or c minus d. What if we want to draw d minus c? What are we going to do?
Do the same thing.
So what are we going to start with?
D.
We're going to start by drawing d,
And then negative C.
and we're going to draw negative c, which goes which way?
Except for the opposite way.
Okay, and we're going to put it at here, starting here, right? And then we're going to draw negative c. I know I drew d not quite flat
Drew
enough.
D like C.
Yeah, so there's d,
I'm angry.
and then c.
Jacob, you're just hungry. Go to cafeteria.
Hey, Jacob, eat a Snicker.
You know how you get when you're hungry?
Better?
No vectors, the birds fly on out there. Okay, so d minus c, yes, no, maybe?
No.
No? What did I mess up?
Oh, no, it's mine. Yeah, I saw it.
Okay. Okay, thank God we get away from the drawings. We can do this algebraically.
Yes.
Algebraic vectors. To add algebraic vectors, you add like components. To subtract algebraic, it's going to be mine. To add algebraic vectors, add like, oh, I'll donate it to charity, but I'll take it away from me. To subtract algebraic vectors, subtract like components. So the sum of u equals equal. Why are there two equal signs there?
Because equal is OP.
I think they're trying to say a not equal instead of, so they just slash this here.
What?
But why would it be equal? But
equal. How?
Oh, okay.
Why don't they just put equal in the slash?
Equal. I don't know. Slash disappeared.
No, I don't, yeah.
because
Okay, equal, but you need to say that.
Let's just get one.
But then we're blind.
The sum of u, which is equal to negative 5i plus 4j, and v, which is equal to negative 7i minus 11j, then u plus v is negative 5 plus negative 7i. So we take the components that are the same, right? The negative 5 plus negative 7, the I values. Take the 4 plus negative 11, giving us negative 12i minus 7j. U minus v, we then subtract. We take negative 5 minus negative 7, giving us positive 2, and 4 minus negative 11, giving us 15. Will v minus u be the same as u minus v? No. Good. Will v plus u be the same as u plus v?
Yes.
Yes. Yes. If a is equal to and b is equal to, then determine a plus b, a minus b, and b minus a. Okay, so go ahead, you can write that out. I will
say state instead of determine.
lag behind. No, I want to see your work.
There's a lot more here.
Sure. A minus B. And B minus A. Left not enough room. So if it says determine and use state, you're going to lose marks, right?
Oh, whoops. A plus B. A minus B minus.
Phew. Whoa. Phew. Thank you. What do you notice about A minus B and B minus A?
They're not the same.
The signs are the same.
Wait, they are the same.
They have the same magnitude but are in the opposite direction, right? I know.
I win.
Column vectors. The addition of column vectors similar. If u is -5/4 and v is 17, -9, then u plus v is you just add them together, and u minus v is you just subtract one from the other, and v minus u will be you subtract the other from the one. And so we are going to determine a plus b, a minus b, and b minus a. What's easier, column vectors or I and j, geometric vectors? Column, right?
It's like we forget these type of errors. Forget what? These type of errors.
Yeah.
Yeah, like the arrows on the ground.
Well, with McKenna, I'll just figure out some general punishment for, we won't take one, like maybe 2 marks off the entire test or something.
Whoa.
That's got to be enough to hurt.
Out of 6.
What if you're writing your IB exam and you forget them and they start dinging you every time you forget them?
That's like one.
It's going to count far more than losing a couple of marks on a test every time you forget them.
We'll do it anyways.
Why would you write them italicized?
It's not italics, it's bold. So if you write them italicized, you lose all the marks.
It's bold, yeah, italicized.
What? What did I mess up?
A minus B should be 5.
Yeah, it should be 5.
It should be 5. So
Yeah.
Minus -10.
You're really bad at math.
That's why I have you here, Grant.
I didn't say it.
Okay. Now is it good? I just did that on purpose, not to see if you were paying attention. Yeah, I know you're not. Your talent's only going to carry you so far. After that, you're actually going to have to start working.
Yeah, I need to make a habit of that before you go back.
Well, there's going to come a point. Now, do you know how to work hard? Do you know how to actually work?
Everything outside of that.
Okay.
Yeah, so.
Good. So when the time comes in math, when you're doing that higher level stuff next year, and you actually have to sit down and do some work,
It can be harder than physics.
then you'll have to know.
Actually, it probably will.
Yeah, well, okay, let me see. My daughter did standard level math and higher level physics, and she liked physics a lot more than she liked math. So. The zero vector,
Physics tells a story.
I know. The zero vector is a vector with magnitude 0. Although the zero vector has no direction, it's convenient to regard it as parallel to every vector. Okay? Just a statement of statement. Well, it's not really there because it doesn't, it's got no magnitude, it's got every direction. Each point, P, on a coordinate grid is defined by a position vector OP, where O is the origin. The position vector of point P can also be denoted by P or P. OP means what?
Overpowered.
Open power?
Overpowered.
Overpower. Also means original poster.
Operator.
Okay, so we can take any point. This is actually important. We can take any point on a coordinate grid and define a vector by drawing a vector from the origin to that point. It's called the position vector. So if P, well, we're going to work with it in a minute, but so if P is at 2, -3, the position vector of P is OP, and OP can be expressed with geometric vectors as shown. It can be expressed. You want to do the rest on your own? You can do. You got the weekend. Why not? I'll shut her down. We're going to do this or not? Okay, so it can be expressed with the geometric vector shown, with the algebraic vector 2i minus 3j, or with the column vector 2, -3. In general, if P is the point xy, then the position vector of P is denoted by OP, where O is the origin, or 0, 0. And OP can be expressed algebraically as xi plus yj, or as the column vector xy. How do we denote the position vector of point Q?
Where is point Q?
Doesn't matter.
Oh.
OQ.
Yes. Oh wow. I get it. Why can't that be IQ?
Or a bold letter Q.
I don't think anybody else can do that.
No, we can't do that.
Or Q. If Q is at -5, 3, then draw the position vector of Q on the grid above. So, where do we go?
The arrows are so small on this. Maybe I should draw my arrows like this. No.
Okay. So we simply go to the point -5, 3. We represent the position vector geometrically. Now we want to do it algebraically in 2 different ways. What would they be? Or? Right, or the column vector.
I think there's a matrix.
It's actually a column matrix, but we don't do matrices anymore, so I don't know if I have, because it's not in the curriculum anymore. Yes.
Why is it lowercase?
Because I'm talking about vector Q. When I talk about vector Q, it's always lowercase. You should pay attention. If you'd have paid attention on that very first page, you would not be asking any of these questions.
Boom. It's a matrix.
I know. I get it now.
Vectors in terms of position vectors. Any non-position vector can be described in terms of the position vectors of its endpoints. So for example, if we have vector A, which goes from, or if we have a vector going from point A to B, which is -4, 1 to 2, 5, then AB is a non-position vector, right? Where does a position vector have to start? Origin, right? Okay. So this vector does not start at the origin. It is a non-position vector. The position vector of point A is OA. The position vector of point B is OB. The diagram on the right shows that if you add AB and OA, the result is OB. Okay, so if you add, it's not so obvious on this.
Oh, I see.
Okay,
Thanks. Well done.
This isn't.
so if AB is added to OA, so if you go OA and then add AB, you end up with OB, right? Mathematically, we say OA plus AB is equal to OB, right? Tip to tail, right? So OA plus AB, the result is OB. Since OA plus AB is equal to OB, then using the subtraction property, vector AB must be equal to OB minus OA. Okay, so for example, AB, which is equal to OB minus OA, is 2i plus 5j. That's OB, right? 1, 2, 1, 2, 3, 4, 5. And minus -4i, 1, 2, 3, 4, plus j, which is 6i plus 4j. Or getting away from this god-awful method and going just to a straight column vector, which is actually a little bit easier, I think, because you don't have i's and j's and everything's floating around, is 2, 5 minus negative 4, 1, which is 6, 4. Okay? So that's AB. In the diagram to the right, use the geometric vectors and the tip-to-tail method to subtract OA from OB. So how do we subtract OA from OB?
Find OA.
You reverse one of them.
Which one?
Oh,
Really? Because what are we subtracting?
I was reading in that.
Oh wait, we're subtracting
Subtract
OA.
OA from.
So we want OB to OA, so
So we're going to do,
Just stop now.
if we want to do OB minus OA, if we want to subtract OA from OB, which is what it's saying, right? Is to subtract OA. This is subtracting OA from OB, which is OB plus negative OA. If I'm going to do that geometrically, then how are we going to do that?
You have to find it.
Let's be.
So how am I going to draw negative OA off of this point? Which way am I going to go?
To the left.
To the right.
To the right.
To the right? How far?
Oh.
The same distance as.
4 and then down 1.
And then?
Down
And it looks like OA except it's just that way.
So this is negative OA. We then take the resultant, which runs here, and this is OB plus negative OA, which we can just write as OB minus OA. And what is this vector? Well, okay, there it is as a geometric. So what is it? It's 1, 2, 3, 4, 6, 6, 4, right? Write the resulting vector as a column vector. So what is the resulting vector as a column vector? 6, 4. Compare this to the subtraction of column vectors above. What do you notice?
Oh my.
Now you get to say,
It's the same.
they're the same. Oh, thank God, we're back on that.
Okay, guys.
They're the same.
Why are vectors so long?
Depends on their magnitude. Yes.
No, you can't.
If A is negative 4, 1 and B is 2, 5, then BA is a non-position vector as shown in the diagram. The position vector of point A is, again, OA. The position vector of point B is, again, OB. The diagram on the right shows that if BA is added to OB, right? So we go OB plus BA, the result will be OA, right? OB plus BA, result is OA. Mathematically, OB plus BA equals OA. Since that's true using the subtraction property, then BA is equal to OA minus OB. Now we've got all of those.
Oh my God, there's so much.
So using, what notation is that? It's not geometric. What's
Algebraic.
algebraic notation. Right, we get the negative 4i plus j minus 2i plus 5j, giving us negative 6i minus 4j. And using the column vector representation, we get the negative 6, negative 4. And counting off of the actual diagram itself, we get, go 1, 2, go 1, 2, 3, 4, 5, 6 left, negative 6, 1, 2, 3, 4, negative 4, right? 6 left, 4 down. In the diagram to the right, use the geometric vectors and the tip-to-tail method to subtract OB from OA. So how are we going to do that? So we want OA minus OB, which is equal to OA plus negative OB. So we're going to need a negative OB off the tip of A. Right, so we got OA. What would minus OB be?
A number.
Left 2.
So this goes right 2, and you go left 2.
Down
1.
Down 4.01.
What?
Okay, so that's negative OB. And this result then is OA plus negative OB, or OA minus OB. Right, the resulting vector is a column vector. So, what are we doing?
No.
6 and
4.
negative 6 and
Negative 4.
And then it's gonna ask for the notice of series.
negative 4. Did I draw that right?
Wait, how are they? Oh, second, they don't start at the origin.
Yeah.
I just realized that.
Oh, yeah, something moved, eh?
Loophole.
Okay, hang on.
Thanks, everyone.
Thank you for pointing
This
that
thing
out.
is so
Okay, here's the origin then.
We just changed the origin.
Yeah, well.
Six, that,
1, 2.
touching it.
Yeah, it's kind of messed up, right?
How dare they do this?
Strong.
But it'll take us to negative 6, negative 4.
Or at least in theory it should.
Yeah, in theory it should. They're the same.
Oh my, really?
Yeah, except the diagram's messed up, but they're the same.
Therefore, they're not the same anymore.
Yeah, they're the same. Same.
I'm gonna write down.
Okay, in general, the vector PQ can be described in terms of position vectors P and Q by the equation OQ minus OP. Okay?
Oh no.
Okay? Yeah? No? Okay. So here, just sketch it out, right? Wherever P is, it doesn't matter where P is, right? So you say here, here's P. That's O. Here's Q. That's OQ. I want to go P to Q, right? I want to go from here to here. I want to go that way, which means I need to go, wait a sec, what am I doing? So I need to go OP.
You need to go OQ.
No, I need to go this way and then, nope, hang on.
Yeah, because the vectors are tip to tail.
Ignore that last, yeah, let's try that again.
Super real.
When does this period end?
Never.
When the bell goes.
I don't know.
OQ.
I think they're lying to us.
No, P to Q.
Yeah.
No, it's P to Q. Because
P to
on the-
Q.
On the first page, when it says
What you can do
P
the pop
and there's an arrow next to each.
11.5.
It gives you the same thing.
P to Q, well, P to Q is this, right?
Yeah.
If you subtract OP,
And if it was QP arrow, then
if you
it would be
subtract OP, it gives you an equal vector. But it isn't.
Oh, right. Okay, so if you go here and then subtract that. All right, what's left on there? Oh, well, good, that's it. Okay, all about vectors. It's all homework.